Our eyes are connected to our brains by big, complicated bundles of nerves. The nerves are so big and complicated that many scientists like to think of our eyes as part of our brains. See? And here is the eyeball. That's right. Your eye is shaped like a ball. And inside is the lens. The lens is the clear part that light goes through. And in your eye, the lens sits way up near the front, like this. Now, before light gets into your lens, we have to control the amount of light that comes into our eye. We don't want to have too much or too little. And we do that with something called the iris. The iris changes size, like this. By the way, the iris is the part of your eye that has color. Like someone says to you, you have blue eyes, or brown eyes, or green eyes. That's the iris, this part right here. Now let's say we're looking at something, maybe a kid on a stick out here. All right, the light from the kid on a stick goes through our iris, through the lens, to the back of our eye. And look, the image of the kid on the stick is upside down. Isn't that wild? The kid on the stick is upside down.
We heard you, Bill.
So our brains take the upside down images from both our eyes, turn them right side up, mix them together, and make sense out of what we see. The same thing that makes this happen makes this happen. And this. It's electricity. Whoa. Well, electricity is the flow of tiny particles called electrons. And they're not just smaller than atoms, they're actually part of atoms. Take a look at this. It's our battery-powered electrical circuit of science. We're going to run this big light with this big battery. Watch.
Attention, Nile Lab.
See, right now, electrons can flow from this side of the battery, through this wire, through the switch, through this wire, into the light, and back to this side of the battery. They're flowing in a closed path, what scientists call an electrical circuit. Now, circuit, that's from an old word for go around. So electrons, right now, can go around an electrical circuit. The flow of electrons is a lot like the flow of water. No kidding. Watch. When I operate this great big water pump of science, water goes through this hose into this box and makes this water wheel go around. And it goes out the other side and through this hose back to the pump. It's a closed path for the flow of water. It's a water circuit. It's just like the flow of electrons through an electrical circuit. Electricity is a very versatile form of energy. The same electrons that are making the light up are making a motor go around. See, electricity can do all kinds of different jobs, and they're all done with electrons.
Whoa, dude. This is awesome.
Definitely. Awesome. I mean, like all those stars. Dude. Oh, there's millions of them.
And like each one of those stars is like a sun.
Like, whoa. Dude. That means that, like, oh, there's tons of other solar systems.
Well, yeah.
Whoa. And that means that we're like little specks. Oh, like almost nothing.
Whoa.
Now, one of the coolest things about dinosaurs is that of all the millions and millions of dinosaurs that must have once lived, we only know about a few thousand. And we know about them because we found their bones. They're fossil bones. Now, fossil, that's Latin for something that's been dug up. So we've dug up dinosaur bones. That's how we know how big they were, how much they weighed, what they ate, even how fast they could run. Now, we don't know all about dinosaurs, but we do know a lot. Now, let's say you're a dinosaur, an Apatosaurus. Yeah, Apatosaurus. and you were walking along, minding your own business, and there was a flood. And you got buried very quickly. You drowned, and silt and mud washed down over your bones and covered you up. Then over time, minerals worked their way into the little gaps in your bones. Your bones became permineralized. Minerals all the way through. Okay, and you sat there for 65 million years! Then, about 100 years ago, a paleontologist comes along. This would be Mary. Looking carefully, maybe poking around. She goes, oh, what's this? And she very carefully brushes away the sand and dirt that you've been buried in. And, oh, look, an Apatosaurus. Yeah, Apatosaurus. Quite a wild time for a dinosaur. Did you know that white light is a mixture of all the colors of the rainbow? It is. Now this is the plastic water-filled prism of science. And shining into it is a bright white light. Now when white light goes into a prism, it breaks up into all the colors of the rainbow, what we call the full spectrum of colors. So down here is the spectrum being made by the prism of science. See, here are all the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and purple, or violet. Now watch. I'm going to try to break these colors up using another prism. Red, yellow, green, blue, and violet. See, they can't be broken up anymore. What that means is, these are pure colors. White light is a mixture of all the colors of the spectrum, but each color is its own color. White light is colorful. About 2,000 years ago, in the town of Alexandria, which is here, near the mouth of the Nile River, what is now Egypt, there was a guy named Eratosthenes, and he was the librarian of the great Library of Alexandria. One day, he came across a note from someone who lived here in the town of Sina. And the note said, at noon on the longest day of the year, sticks cast no shadow, and we can see all the way to the bottom of our wells. Eratosthenes realized that where he lived, sticks did cast a shadow, and he couldn't see to the bottom of wells. And he got to thinking about it, and he realized, the earth must be round. Yeah, we must be living on a big ball. That's the only way for there to be no shadow here and a shadow here. So he measured the shadow that the stick cast, and then he paid someone to walk from Alexandria to Sina and keep track of the distance as carefully as he could. Well, that distance turned out to be around 800 kilometers, and the shadow was about a 50th of a circle. So then he multiplied 50 times 800, and he got 40,000 kilometers, and that's the distance around the Earth, what we call the circumference of the Earth. So check this out. This guy made observations of a star, our sun, and he figured out the size of a planet, our Earth. The same kind of observations that you can make. Hey, not bad. What makes one atom different from another?
The number of protons in the nucleus?
The number of protons in the nucleus. Take a look at this piece of metal. It's shiny, like silver. Now here's another piece of metal. It's shiny too, but it's a little bit orange colored, like gold. Now this material turns out to be aluminum, and this material turns out to be copper. Now the main difference between this material and this material is
The number of protons in the nucleus?
the number of protons in the nucleus. You can see and hear the differences.
Bill! Hey!
Now, scientists have grouped all the different materials, all the different elements that we can find into groups, which have come to be called periods. And we've arranged the periods on a table, the periodic table. So let's go to the chart.
The periodic table.
The table.
Yeah.
The periodic table.
Uh-huh.
Voila! The periodic table. See, every element has a name, and you know most of them. They're familiar. There's carbon, oxygen, aluminum, copper, iron. They're familiar. But there's some weird ones too. There's like erbium, palladium, and krypton. Scientists have given each element a 1 or 2 letter symbol and a number. Now, that's not just any number, that's the atomic number.
The number of protons in the nucleus?
The number of protons in each nucleus. Now, there are 92 elements that occur naturally. And using these elements, we can make all kinds of interesting molecules. How did life get started on Earth? Where did evolution begin? Well, near as we can figure, the ancient Earth was covered with the ocean a little over 3 billion years ago. And the ocean was a sort of primordial soup that living things got started in. Now, primordial, that's an old word that means very old. See, scientists have done a famous experiment with primordial soup where we cook it. The experiment would look something like this. Put primordial soup in a big flask, cover it with what we believe to be the ancient Earth's atmosphere, which would be ammonia. And ammonia is the same stuff you smell when you clean a window. We cook it by heat from the sun, and this would be freshwater rain, which would come out of this boiling flask right here, and lightning from primordial thunderstorms. The thunderstorms make the molecules change and rearrange themselves. And eventually, we have found that we can reproduce tiny pieces of deoxyribonucleic acid, tiny pieces of DNA.
DNA,
The very building blocks of life
the blueprint for future generations.
can be made with an experiment somewhat like this one. So the primordial soup was very much like the ocean is today. Look at all these living things. The ocean's full of them. You and I are living things. The primordial soup is still cooking. Living things evolve, living things change, but not that fast. Now here's a dam that humans put here, and over here is a fish ladder. And here's the idea. Fish can swim from step to step and get up the ladder and get up past the dam. Do you see what I'm saying? But do you see one fish? One big salmon over there? I mean, salmon are big. You see one? Not one. I mean, salmon are like this. You think I'm telling you fish don't? They're big fish. If they were over there, you'd notice them. And some people say the sea lions are eating them. Well, the sea lions might eat a few fish. Maybe they eat a lot of fish. But they don't eat this many fish. I mean, it's a lot of fish that aren't getting past the dam. They aren't getting up the steep of this fish ladder because humans have changed their environment. Humans have let silt come downstream, chemicals get in the water, they dam the stream up altogether so the salmon can't swim past. And you know what else? It's not one person, millions and millions of humans slowly degrading the streams, made the environment not so good. So you got no salmon. You know what I'm saying? Because humans have changed the environment. Now, a fish could adapt. It could evolve. But it would take millions and millions of years. It's not going to happen in 100 years. It's not going to happen in a weekend. It takes a long time. Humans have changed the environment faster than most living things can keep up.
Oh, great. Science! Thank you all. It's so good to see you. Unlike, I believe, all of my colleagues, I am an engineer. I mean, let me emphasize, like my colleagues, I'm a human, but engineer. So my older brother, tremendous influence on me, had a wonderful physics teacher, Woodrow Wilson High School, Washington, D.C. And he told my brother the story, who told me the story. Michael Faraday, in 1828, then through 1831, would do the Christmas lectures in London, which is back east someplace. And he did this demonstration where he had a coil of wire on one end of a laboratory bench connected to another coil of wire by two wires, the terminal wires of the coils. So he goes down here with a bar magnet, reasonably powerful magnet, which you could find in those days. So he moves the magnet at this end of the table, and the compass needle moves at this end, as if by magic. Of course, it wasn't magic, it was science! Yes. So the story was embellished. And it was presented to me that he did this demonstration with such success so often that he presented it to the Queen of England. And the Queen of England is supposed to have said to him, "Mr. Faraday, of what use is it?" And here's where I just admire the guy, and I admire what we in the United States perceive as the British way of thinking. He did not say, "Lady! What? Are you, would you look? That's at that end, I'm at this, I'm not touching it. What? Are you high? I mean, come on. love it. You like it. But that's not what he said. According to the story, he said, "Madam, of what use is a newborn babe?" Now, I don't know how much time you have spent with newborn babes, but they're not that useful. They're loud, and they leak, and there's a lot of times they don't seem to understand a word you say to them. Look around, everybody. Everything in this room, everything, the lights, the curtains, the paint, the clothes you're wearing, the upholstery, the floor, the stage, everything here owes its existence to that discovery, to the discovery that not only is there a connection between electricity and magnetism, but there's a connection between electricity and the moving of the magnetism, the flux. And that discovery, dare I say it, changed the world. But this process of science that this guy spent, I guess, he took tremendous pride in his demonstrations, and he really perfected this to show it to people. This discovery had a deep effect on me. Now, when I was a kid, I delivered the newspaper. I was a paper boy. That was the title. And in the Washington Post on Sundays, there'd be Ripley's Believe It or Not. And it's still there. It's a different paper, but still there. And it would say from time to time, they would run the story roughly, according to aerodynamic theory, bumblebees cannot fly. And this made quite an impression on me. And I spent some time watching bumblebees. And it became clear to me that the bees are fine. The problem is with the theory. And then I realized that I could influence objects. I realized that if you could understand things enough, you could make things and shape things and imagine traveling around the world. And you could do it with a balsa wood airplane. Just think what you could do if you worked for a big company like Boeing. And that's what I ended up doing. I worked on 747s. Relax, everybody. I was very well supervised. But these things that happen to you when you're a little kid influence you so much. And I'll bet you everybody in here who's a science enthusiast got excited about it before you were 10 years old. And this passion, this drive to know our place in the universe is what makes us special. It's what makes our species worthy. And with this PB&J, this passion, beauty, and joy, we can, dare I say it, change the world. Thank you.